Vibration and acoustics, understanding harmonic excitation. Imagine a guitar string vibrating when plucked or a bridge swaying gently in the wind. These are everyday examples of harmonic excitation, where forces act in a regular, repeating pattern. When a mechanical system experiences a force that varies sinusoidally, or in a smooth wave shape, it is said to be under harmonic excitation. This causes the system to vibrate at the same frequency as the applied force, creating what we call forced vibration. The system's response is also harmonic, but how big the vibrations get depends on several factors. In mechanical engineering, understanding how structures and machines react to periodic forces is essential. For example, imbalanced rotating parts in engines produce vibrations at specific frequencies. Bridges and towers face oscillations from steady winds, and vehicles traveling over uneven roads experience vibrations at certain frequencies. These forces can be modeled mathematically using equations of motion. For a simple mass spring system without damping, the equation looks like this. The mass times acceleration plus the stiffness times displacement equals the force amplitude times the sine of the excitation frequency times time. The solution to this equation has two parts. One is the transient response, which fades away over time. The other is the steady-state response, which continues as long as the force is applied. The steady-state vibration is harmonic and matches the excitation frequency. How large the vibrations become depends on how close the excitation frequency is to the system's natural frequency. When these two frequencies are near each other, resonance happens and vibrations can become very large. Damping, which is energy loss in the system, helps control these vibrations and prevents damage. Engineers use frequency response functions to see how a system reacts to different frequencies. These functions help predict when resonance might occur and guide design choices to avoid excessive vibrations. For example, in designing machinery, engineers select components with natural frequencies from the operating speeds. In vehicle suspension design, they tune the system to reduce vibrations from road bumps. Structural engineers analyze how wind or seismic activity can excite certain vibration modes, which is vital for safety. Vibration modes are specific patterns a structure can vibrate in, each with its own natural frequency. When harmonic forces match these frequencies, particular modes get excited more strongly. This is especially important in modal analysis, where engineers identify which vibration modes are most likely to be triggered. Understanding harmonic excitation helps in designing systems that can withstand or avoid resonance, ensuring safety and longevity. In summary, harmonic excitation is a repeating force that makes systems vibrate at the same frequency. The response depends on the relationship between the excitation frequency, the system's natural frequency, damping, and force magnitude. Recognizing how these factors interact is key for controlling vibrations in machines, vehicles, and structures. This knowledge helps engineers create safer, more reliable systems that perform well under periodic forces.